Well, first of all, there are several evaluation and demo boards with Xilinx FPGAs to choose from. Many are made by Xilinx. These usually have the most features, target the largest devices, and are the most expensive. But most are made by Xilinx partners, and there's a short list of these shown here. Well, actually, this is most of them. And those include Avnet, New Horizons, and Digilent. We provide detailed information about each of the available boards on our website. Each board may have different components that you may need, as well as support a Vertex or a Spartan device family of your choosing. This will directly affect the cost of the board. Now, on this slide, we see some of the more popular demo boards, specifically the ones we use in a couple of our classes. The first is the ML507 that supports Vertex 5. We also see the 1600E, which is not necessarily the most popular by any means, but is one that we support in our courses, which uses a Spartan 3 device. And one of the newest boards is the Spartan 605 or SP605 board. As you may or may not know, the base system builder is designed to make building an initial project quick and easy. It simply allows you to select the demo board of your choosing and quickly build an embedded system through a series of GUIs targeted to that demo board. The BSB is designed to work with all of the currently available demo boards. However, if your tools do not support the board you want, make sure you go to our website and download the necessary board information from our website. This is because not all the board information is available at the time of the software release. As you can see, creating a project is very easy. You can select File, New Project, and then choose to use the BSB utility or to create a starting project. Remember that the BSB utility allows the user to create a design targeted for a specific demo board. The blank project button is used when a customer wants to create a design from scratch and is not planning on using a demo board that is currently available. When you select to create a project and new design using the base system builder, you'll be asked a series of questions about the project, such as what demo board, what processor, how do you want to configure the processor, what I/O interfaces are you going to use, what peripherals do you need, etc. Now, this is possible because, of course, the board has already been made. So if there is an SDRAM on the board, it makes sense to make it easy for a customer to add an SDRAM controller onto the PLB bus, right? Right. Now, after you've answered all the questions, your MHS file will be made for you. You may not recall this, but the MHS is your entire hardware design in a single text file. This is what is changed by EDK when you modify your hardware design. All of your peripherals and their chosen options are also stored in this single text file. I mention this because the MHS is user editable, although it is not necessarily recommended for that use. But I still encourage you to crack the file open and have a look. The syntax is pretty simple. Now, the BSB will also create a test app file which contains a simple C source code to test your hardware and is ready for download. The base system builder will also generate a UCF file which contains your final pin assignments and pin attributes as well as timing constraints for your demo board. Now, it is a standard file used in all FPGA designs. Like the MHS, I encourage designers to open this file as well and review its contents. Like the MHS, it is user editable, but is easier to change when you use the Xilinx Constraints Editor. But that is accessible from the ISE tools, not from within EDK. The UCF file also contains your design's timing constraints. These are used to communicate to the implementation tools how fast you want the parts of your design to operate, and most specifically, it's going to make a global constraint for each of the clock domains. So if your processor system has two different clock domains, one for buses and peripherals and one for the processor, then the tools are going to have a timing constraint associated with each when you use the BSB. So this is a good thing. It's going to save a lot of effort and a lot of understanding. Now, as you can see from the lower screenshot, you can also specify a peripheral repository directory. Now, this is useful if you have built a library of custom peripherals that you may want to add to the design later. Well, if you haven't, most likely you're going to want to do that. Most customers do want to build a custom peripheral to add to their embedded system down the road. Now, we cover building and optimizing a custom peripheral as part of our standard embedded system design course. But once you've made that IP, a lot of customers like to make that IP available to all their designers, and so they'll use this repository to keep all that IP. Now, after you've chosen your board, the next step in the base system builder is to select the demo board with the GUI. This GUI will then also quickly allow you to learn more about all the available demo boards, since all the technical information about each demo board is already installed. So as an FYI, One of the things you can use is use the base system builder just to shop and find out the different demo boards that are currently available and go through and learn about all their features. Now, the BSB also makes it easy to install the necessary BSB information for the most recent and thus not installed demo boards. You can even customize the BSB to create your own custom demo board if you would like. Now, we're not going to have enough time to go through all the GUIs that are supported with the BSB, but suffice to say there's about 8 or 9 pages of options to modify for your demo board. Now, I want you to note at the top of the screenshot there's a little green dash bar at the top. That tells you where you are in this process with the BSB. It allows you to build both a microblaze as well as a PowerPC 440 embedded system. You can also build a dual processor system. This could include multiple microblaze or PowerPC cores, or even one of each. Now, as you can see, the GUI then shows you a representation of your system so you can better understand the resources that would be involved. The BSB will even ask how you want your peripherals connected to the buses and which peripherals should be shared. Pretty smart, eh? That is important because the PowerPC 440 has different ports for connecting a master or a slave bus, and how you set up your system will determine whether or not one peripheral or master device can communicate with another. So the implication is that the BSB is going to make it easier for you to build an embedded system that you can actually use. Now, also keep in mind that the ability to use the PowerPC 440 processor, again, is still dependent that you're going to be purchasing a Vertex 5 FX device. Depending on your processor, you'll then be asked to configure the processor. One of the most important options is the clock frequency that you plan to connect the processor to. The GUI will allow you to specify a different processor and bus frequency if you're targeting the PowerPC 440. But don't forget that the requirements for your bus frequency are dependent on the PLB V46 bus standard. So generally, most integer relationships between the frequencies are supported, generally 1 to 4, where the highest frequency would be connected to the processor itself, say the processor at 400, and the lower frequency to the buses, say 100. The BSB in this case will also write a global timing constraint for each clock signal in the UCF. That will guide the implementation tools to manipulate the place and route solution so the system timing can be met. But the real question again is how fast will the system run? The answer is that it simply depends on the number of peripherals and how many buses your design has. Simply put, more logic, the lower the maximum speed. It also depends on the family of the FPGA you're targeting and of course the speed grade. Recall that each family has different performance. However, to get peak performance, most designers are only adding a couple of peripherals to the system. If your system is like that, then top speed should not be that difficult. But unfortunately, you won't know until you build the hardware and try to place and route the design. Fortunately, using the base system builder to build your system is very fast. So typical system hardware can be built in under 30 minutes. Now all you need to do is add the rest of your FPGA design to the logic and then go through place and route. And of course, depending upon whether or not you have that remaining logic, will determine how fast that will actually run through implementation, how fast the system will be. Now lastly, note the debug interface option at the bottom of the GUI. This allows you to insert access to your embedded system through the FPGA JTAG chain, which is recommended for the PowerPC 440. Now this is done with the addition of a simple component in the MHS file called the JTAG_PPC block. By asserting this button, it will be included and hooked to the FPGA internal boundary scan components for visibility on the FPGA's JTAG pins, which is necessary for software debugging. So basically what it does is it connects together the FPGA's JTAG chain as well as the PowerPC's JTAG chain. This GUI allows you to add peripherals to interface to the various components your demo board has. So for example, if you have a series of push buttons or LEDs, you'll have the option to add a general purpose I/O peripheral to your system. In this case, only the peripherals that are available for this demo board are available in the left-hand column. To add a peripheral or external memory controller, simply drag it from the left-hand column to the right-hand column. To modify the core's parameters, you can simply double-click it after adding it to your system. Note that not all of the I/O interfaces are required for you to use. Likewise, internal peripherals, that is, those peripherals that don't connect to I/O pins, can be added to any design on any demo board, of course as long as you have enough FPGA resources to add the component. Now, most peripherals support the use of interrupts, and EDK supports you adding a custom interrupt controller, and that is one of the labs as well as one of the discussions we have, is part of our standard embedded system design.